In this video, I'm going to talk about limit of detection, LOD, and limit of quantitation, LOQ. So let's start out with a problem. 10 readings of a blank solution results in an average signal of 0.003 with a standard deviation of 0.001398. When a sample is analyzed with the same method, it results in an average signal of 0.006. The question is whether or not the signal from the sample, the 0.006, represents a signal from the analyte or not. It may seem like it's definitely larger than the blank, since it is twice the size, 0.006 versus 0.003, but it's not quite that simple. That is an average blank value with an associated standard deviation, so there is some variation in the blank signal. So we need to know if the blank from the sample is part of the population of the blank signals or if it's different. To answer that question, we need to know the limit of detection of the method. We'll come back to this problem again at the end after we talk about both the limit of detection and the limit of quantitation, what they mean, and how to determine each of them. Let's first talk about the signal you might get from an analysis and what they might look like. The figure on the right shows 3 examples of a signal from an analyte which is represented by the peak. It's quite obvious in the top 2 plots that there is a signal from the analyte, but it's much less obvious in the bottom plot. You may even say that there is nothing present in the bottom plot because the noise is nearly as high as the peak, where the analyte is expected to be. So in the second plot, this is an obvious peak. In the third plot, we might assume that that's the peak, but if we didn't have the analysis or the plots above that particular sample, then we wouldn't know that that is where the sample is supposed to be located. If you just took that by itself, it looks like it's all pretty much the same. So it's really difficult to tell whether or not that signal or that peak in the third plot is actually a peak or if it's part of the noise. Ideally, there'd be no noise and the signal would be smooth, kind of like the top plot. But in reality, especially when dealing with small concentrations of analyte, noise from several different sources is something we just have to deal with. The important factor to consider is the signal-to-noise ratio, which tells us how large the signal is compared to the noise. The larger the signal-to-noise ratio, the easier it is to distinguish the signal from the noise. So for example, in the top plot, the noise is very small because there's not much variation in this part of the plot. It's pretty smooth, pretty flat, and it's really easy to see that peak. As we go to the second plot, it's still easy to see the peak, but you can see that the variation in the noise is getting larger. That could mean that the method itself just has a lot of noise, or that the peak or the analyte itself is at such a low concentration that it's getting closer and closer to being the same magnitude as the noise. And that's sort of what's seen in the third plot, where the noise is very similar in intensity to the signal, supposing that that is an actual signal. So to determine whether an observed signal is from the analyte or not, it has to be statistically distinct from the noise. The limit of detection is the minimum concentration or mass or signal that a method can see with a known level of confidence. In other words, the signal from the analyte has to be some amount higher in intensity than the signal from the blank. Now, if you analyze the blank a number of times, what you're essentially doing is determining what the signal of the method would be in the absence of analyte. So that is a good indication or a good measurement of the noise of the method. So for limit of detection, we want to be able to say with certainty that the signal that we see in a sample that supposedly has analyte is definitely from the analyte. And at the limit of detection, we cannot be certain of how much of the sample analyte is there, since the uncertainty is going to be very large, right? The signal is going to be very close in intensity to the blank, so it's going to be very difficult to determine the difference between the variation in the blank and the variation in the sample, or the analyte. But at the limit of detection, we can definitely say that the analyte is there but it's going to have a very large uncertainty associated with it, so we can't really say exactly how much is there. There could be 100% error in that analysis or 100% uncertainty. So this is because the signal at the limit of detection is very noisy, and to determine the minimum signal required to be sure that it's from the analyte, we use this equation here. Okay, where the signal at the limit of detection is S sub LOD. Capital S BL is the signal from several measurements of the blank. Lowercase s sub BL is the standard deviation of all those blank measurements. And K, in this case, for limit of detection is going to be 3. And basically that tells us that the signal from the analyte has to be about 3 times larger than the signal from the noise in order for us to determine with confidence that the analyte is actually there. So typically for a blank you would take 10 measurements. More is better to get a good idea of the statistics and what that variation is. So the signal determined from this calculation tells us the minimum signal we have to observe for us to be 95% certain that the signal is from the analyte and not simply random chance. So that peak that we see, that signal that we see, is definitely the analyte and is not a random chance. If we wanted to determine the minimum concentration rather than signal of a method that we can detect, the calculation's a little bit different and it looks kind of like this. So LOD is going to be 3 times the standard deviation of the blank divided by the slope of the calibration curve. So M as in y equals mx plus b. Now the limit of quantitation is slightly different. It's the minimum concentration, mass, or signal the method can reliably quantitate. In other words, at the limit of quantitation, at the LOQ, we can be confident about how much of the analyte is in the sample. Remember, with LOD, we can say that the analyte is present, but we will be very uncertain of its concentration. Whereas with LOQ, we can say the analyte is both present and we can be more certain of its actual concentration. The calculation and the way we go about determining the LOQ is very similar to the LOD. So we have a very similar equation. The difference being is that the K, in this case, is going to be 10. This means that the signal has to be much greater than the noise. If we compare it to the LOD had to be statistically different from the noise to be able to say it's present, the analyte is present, whereas with LOQ, the signal has to be much greater than the noise so we can more reliably quantitate it, more reliably tell how much is there, and have a reasonable amount of uncertainty. Not like 100% uncertainty, maybe 10% uncertainty, maybe 5%, something like that. Okay, so at the LOQ, we're 95% certain that the analyte is present and at a specified concentration, whereas at the limit of detection, we're only 95% certain that the analyte is present. So this slide just shows an example of what different amounts of noise can do to your limits of detection, right? Your vision, how you can see each of these letters on the background. So the darkness of the letters in each of these squares is the same. The only difference is on the left we have a lot of noise, and on the right we have just a little bit of noise. Now you can probably all see the S and P in both sides pretty easily. The R is pretty easy to see on the right side. You can probably guess that it's an R on the left-hand side too, although maybe you might think that it's a B or something similar. But if you look at the Q, I assure you there is a Q on the left-hand side. But since the noise is very large on the left-hand side, you can't distinguish the signal from the noise. Whereas on the right, the Q is much easier to see because the signal from the Q, the darkness of the Q, is much greater than the noise around it. So if these were two different methods for determining high concentrations represented by the S and the P, and then lower concentrations represented by the R and the Q, you can see that a method that has a lot of noise, the one on the left, is not able to reliably detect the presence of all the different concentrations of analytes or all the different darknesses of the letters. So if a method has a lot of noise, it's more difficult to measure lower concentrations. If a method has a lower amount of noise, it's a little bit easier to determine those small amounts of analyte concentrations, because remember, as we're getting at lower and lower concentrations, the signal is getting lower, and the closer it gets to the signal of the noise, the more difficult it is to detect it. So the lower the noise of the method itself, the more easily that you can use that method to determine concentrations of small amounts of analyte. And so now let's revisit the question from the beginning. Is the signal from the sample sufficiently different from the blank that we can be 95% certain that it is from the analyte? So let's do a calculation to try and figure this out. So if we're trying to figure out the limit of detection, so LOD, and then we're looking for the signal, right? Because we're given a signal, and we're given a signal of the supposed sample that may or may not be the analyte. So the LOD is going to be the signal of the blank plus 3 times the standard deviation of the blank. So the signal of the blank is 0.003 plus 3 times the standard deviation of the blank, 0.001398. And if we do that calculation, we end up with a limit of detection, or a signal limit of detection, because we're talking about signal, 0.007194. The last 3 decimal places there don't really matter, because we only need to know if the number is different than the 0.006 from our analyte, or our sample. So what does this mean now? We're comparing the 0.006 to the answer 0.007. So the limit of detection in this case is greater than the sample analyte. So the limit of detection in this case is greater than the signal from our sample. So if limit of detection tells us that that's the minimum signal that we need to be sure that the analyte is present, what can we say here? Well, we can't even say that the analyte is present, because the limit of detection is greater than the signal from the sample. If the signal from the sample was 0.008, then we could say, yes, the analyte is there. It's going to be very close to the limit of detection, so it's probably going to have a high amount of uncertainty associated with it, but we can still definitely say it's there. If we wanted to calculate the limit of quantitation, we could do that as well. And if I remember right, I think LOQ ends up being something like 0.016. So if the sample had a signal of 0.016, then we could be certain of its concentration. Now, what can we say with the current results? So it's a limit of detection of 0.007, a signal of 0.006. If we're asked to report our findings, we could only say that the analyte, if present, is at a concentration that is less than the limit of detection. Okay, so we're not saying it's there, we're not saying it's not there, we're saying if it is, we can't detect it. We might have to use a different method that is able to detect lower concentrations of the analyte. So that's all I have for this chapter. If you have any questions, you know where to find me.